So today we're going to be looking at the hydrogen wave function. And so the hydrogen wave function is really important in chemistry and physics because it is the simplest atom and it is the wave function that kind of has the simplest form that is also an element. So simpler wave functions than this tend to be toy models, and this is the first one that it is actually something that you can use for other things, and it also is a model that tends to be used for other atoms as well. So if you calculate out the orbitals for a hydrogen atom, those are kind of similar looking orbitals for all of the basic elements. So the kind of s orbitals and d orbitals, those are all things that we can see within the hydrogen atom and the hydrogen wave function. And so it can give us an idea of how those elements work together. And so in order to show this is wave functions in quantum mechanics are a pretty difficult thing to plot. And so we're going to need to be a little bit thoughtful on how we want to visualize this information. And so one way that we can do that is we can take it on a grid. So we can plot out a grid and then we can adjust the points on that grid to the size of the wave function. And so we can make them larger or smaller based on that wave function. And so one of the problems that comes up with this method of showing the wave function is that grids have a pretty well-defined structure, and so a lot of that structure might end up being visible within the visualization. So that means that it'll be very easy to see the grid, but it might make it a little bit more difficult to see the actual values that we're looking at. And so another idea that we could have is, well, since a grid isn't working super well, maybe if we do a grid in spherical coordinates, that'll make it look a little bit easier to understand too, because hydrogen atoms are very spherical, we might end up getting a better point of useful points versus not useful points in our diagram. So we can look at that. And we also notice that this as well doesn't visually look like what we would like it to. We end up seeing more of the grid than the actual underlying wave function. And so a third method that we could think of is maybe if we use a random grid, that'll end up being more helpful. So if we use a random grid, one of the problems that comes up with that is that we end up with these clusters of points, and that can end up making it look like there is information where there is not information. So random grids also have another problem. So basically with a random grid, what we're doing is we're just randomizing the points and then we're using those points as the grid. And yeah, that has the problem of having unexpected clustering. And so there's this fourth solution that I can think of. So just to be clear, there are more than just these few solutions. So there's this other idea that comes from astronomy that is very useful for when you want to make your grid not have any sort of initial information. So this comes out of n-body system. When people make simulations of gravitational simulations, oftentimes they want their initial conditions to be unbiased. And especially when they're trying to visually identify what will happen, it's really useful to be able to control the initial state of your simulation. And so one of the methods that astronomers sometimes use for this is they will do what they call glassing the grid. And so basically what this is using gravity in reverse. So kind of using gravity but then inverting it, and then playing that forwards a few times steps. And what that'll end up doing is it'll end up making your grid a little bit more glass-like because all the points have a distance from each other, but they also won't be as grid-like because all of the forces will push those particles into their lower energy states, which if you think about it, a grid is not the most minimal structure that you can have. And if you have any sort of small disturbances, the grid will end up breaking down and you'll end up with this more glass-like structure. And this glass-like structure is actually pretty good for visualizing things in 3D as well, because all of the particles are non-random, but they're also spaced very similar distances apart. So you don't end up with the same clustering that you would have in a random distribution. And so glassing methods are really helpful for that. The symmetries from the hydrogen atom can actually give us an idea about how chemistry as a whole works. So the fact that it has kind of these like 2, 4, 8 symmetries that electrons tend to gravitate towards can kind of help us get an idea of why the elemental table is the way that the elemental table is. And so being able to see that in AR is really neat because a lot of these things don't project too well onto a flat surface. So like there are a lot of images of hydrogen atoms on a flat surface, but it doesn't give you the same sort of idea of how it actually looks. So we have this hydrogen atom working now. It's good to compare against other visualization tools. You can see the same types of things that you would in other visualization methods. Sometimes it's too vague or the grid might end up being too opaque and it might block off certain pieces of information. So it's helpful to look at other tools and see whether whether you can see everything that you need to see within our method. So the other reason why I was kind of interested in doing this particular project is the hydrogen atom is a fairly time-intensive process to calculate. So it takes a little bit of time in order to calculate it, especially when you're doing this over a grid-like space. So if you're doing this 20,000 times, it ends up taking a noticeable amount of time to do. And so if you are doing this in a normal AR situation within webxr, it'll end up blocking up the thread, and that'll mean that your usability will break during that time where it is doing the calculations. And so this is a nice project to introduce web workers and multi-threading on the client side. So JavaScript is generally single-threaded. So there is one part of the computer will end up running and it'll just do all these computations. And if anything gets in the way of that, it'll just do those computations instead. And so normally this isn't noticeable because JavaScript is quite quick and usually computers are very fast. So it tends not to be noticeable. But when you have very heavy computations, that single-threadedness can be blocked. You never want to block while you're doing webxr because it has a bunch of calculations that it's continuously doing. And so you don't really ever want it block. And so this is a good point to introduce the way that the web resolves this. So on the client side, there are these things called web workers. And if you use a web worker, you can do heavy computations on a second thread, and then you can message that thread to give it information, and then it can message back to get the information back to your main thread. And so basically what we're going to be using is the fact that there's usually 4 to 8 CPUs on modern cell phones. And so we can use that to speed up our calculation. Okay, so to start off with, we need to import a texture because textures take a little bit of time to import. And then what we're going to need is we need to create the hue, saturation, and luminosity to RGB value because hue is a very useful tool for changing color without changing any of the brightness aspect. So we're going to be doing some of our graphing with hue instead of RGB. Then we have to import our grid, and our grid is just going to be a JSON file that we have in our HTML. Next up is the entire skeleton. This is the thing that we've been using a lot, so it's a lot of code at once, but you should be fairly familiar with this code now. We're going to be using it quite a bit. It's just about 100 lines of pasting that we're going to be doing. Then what we have to do is we have to do kind of a standard buffering geometry. So we have the geometry, the float arrays, the values that we put into those float arrays. The one thing that's going to be a little bit different this time is we have to break it down a little bit. So there's some stuff with the indexing and modulus that you might need to do a little bit extra thinking about. Also, we are going to be animating. So the new colors and the new sizes are going to be the values that we are animating towards. So that's why there's some extra values there. So basically our theta and r are going to be the values that we get calculated out for our wave function. So all the wave function information is going to be encoded into our r and our theta, and those values are going to get moved into RGB for our 4.3JS. And then we just have kind of that standard, putting those into the geometry with our material and then adding those to the scene. Okay, so now we need to do the communication with the actual worker. So we haven't done any of the math, and the math is going to all be encapsulated in the worker. So all of our numerics are going to go there. And so we will start a new worker, and then we will assign a post message to it. So this will send the worker that information. So we'll send it the grid. And then we will also describe the update element, and we will add an event listener to that. And when that gets clicked, it will capture the ML and N value, and it will send that to the worker within the onInput function. And then we will write a listener from the worker so that when the worker is finished with its work, it'll send this information back. And so this will update the scene that we have by updating the new colors and the new size. And then during the render, we will check for if it's animated. And if it's animated, we will lerp ourselves. So we will do a linear movement towards the new color. So we're taking the old color and we're slowly moving towards that value. And once we've done that about 200 times, it's going to be close enough to the new value that we can stop animating. And so we will stop our animation. Okay, so now we'll write the web worker. And so we'll start by importing a script. So we are going to be needing to use some more advanced math. So we'll have to import a math library. Then we will build out some basic tools. So we'll build out some conversion tools between spherical and Cartesian coordinates. We will initialize our values. So we have a few things that we're going to be saving along the way. We will write a complex number to polar converter. So we are going to be using some complex numbers, and we want those to be in polar coordinates afterwards. Then we will write out our messaging function. So this is what's going to be communicating with our main script. And so we have two different types of events. We have starting events and the grid. So when we initially give the grid over, so there's a few things that we have to write out before we actually start iterating over all of the grid. So we want to save some common measurements that all of our values will have. So all of our values will have the same Laguerre polynomial and Legendre polynomial grid. The harmonic scale and the normalization will also be saved across all of the grid points. So then we're going to send the grid outward. afterwards, but right now it's an empty grid, so we'll have to fill that grid up. So we will start by just getting the different points from our initial grid, and then we will convert those into spherical coordinates. So from Cartesian to spherical. Then we'll make sure that there's no nans, which is just, this is a JavaScriptism. And then we will put all of our values into the wave function that we will create in a moment. So we don't actually have a wave function value yet. Then we will turn that value, a wave function is a complex number, so we'll convert that into the radius and the phase. So we'll separate out the phase and the radius. And then we're going to go into the start function, and the start function will look very similar, except for this time we will be reading the L and the M's values that we get from our main script. So those are the values that are inputted, and we will basically do the exact same thing where we will write out all the kind of standard values, and then we'll iterate over the wave function. So now it's time for us to actually write out those different objects. So we have about 5 objects that we need to write. We will start with the wave function, and the wave function is something that we will just get from Wikipedia. It's a pretty straightforward thing. So we calculate out the density, and then the density gets put into first our Laguerre polynomial. So that's something that we have to evaluate with regards to our density, and our spherical harmonics is the next thing we need to get. So we still have to write that function out as well. And then we will have all of our values that we'll put together, and then we'll send that back. So now to the spherical harmonics. Spherical harmonics take Legendre polynomials. So we are going to need to use our Legendre polynomial and evaluate it with respect to cos theta and the phase, and then we will return that value. So that's our spherical harmonics done. Next up is we are going to need to create the normalization value. And so this is a value that just comes from integrating and standardizing all of our values so that they get close to 1. And then we will get the harmonic scale value. Okay, so now with our Laguerre and Legendre polynomials, these are a little bit different. What we need to do is we have an expression, and then we need to differentiate that expression a number of times before getting the right polynomial. And so both of these are very similar. We have an expression, we differentiate that expression for a set amount of times, and then we return that. And so this is why we need to use the math library. The main reason is to do this differentiation. You can do it with some other methodologies involving recursive relations, but it's a little bit more complicated, and it's not necessarily more complicated, but it's a little bit more work, and now we don't have to do that work.